Hi, everyone. Welcome to this session on the last day of Unite. So we're going to talk about how to glow up the graphics with Unity 6.3 LTS. This is the third episode of some talks that we've done with Damien and Oliver to cover like all the graphics performance and visual improvements in Unity. So if you want to watch them, we had one at GDC, we had one at Unite Lakes last year. So my name is Matthew Mueller. I'm the lead product manager for the graphics engine. And Oliver and Damien are in my team. Damien takes care of the platform graphics and Oliver of the render pipelines. So there are things that we are showing that might come a bit later on in the future, so don't take business decisions around it and so on. You probably have seen this a few times. And we will cover mostly Unity 6. Who is using Unity 6? Wow, that's really cool. 6.3 LTS? A bit less people. OK, so it's good. Yeah. So this talk really will cover a lot of the things which are coming in Unity 6.3 LTS, but there will be also things that are actually working in previous versions as well. So in Unity 6, we had multiple missions. The first one was to make it easier to use and easier to onboard, and also to accelerate your iteration time by knowing how the features are working. You know, we've been adding tons of features in the past 5-10 years, and sometimes people were like, we know that it's great, but we don't know how to use it, how to configure it, what it can do, and so on. So we've been adding a lot of samples, URP3D samples, but also samples on the package manager. Actually, who knows here that there are samples in the package manager? OK, so I'll show you, because half of the people seems to be doing so. OK. Yeah. So you can find them here if you go on Package Manager. OK, it's going to load. If you go on Package Manager and, for example, you choose a URP, you have a Samples tab here where you can find some nice samples. And, for example, if I go to Shader Graph, we have tons of samples. For example, the node reference gives a shader graph for each node of the shader graph, explaining how it's implemented and how you can use it, for example. We have also tons of new samples for terrain shaders, custom lighting, and so on, which are ready to use. Some of them ready to use in production, like the production-ready shaders, for example. It's really nice. Then, sorry, going there.
Unity C.
OK. So we've been doing a lot of improvement here, as well as making it easier to use and to integrate all your effects with Unity. You know, we wanted that you can really customize most of the graphic things with Shader Graph. And there were some missing things. For example, no terrain support, no UI toolkit support, and so on. That's all things coming in 6.3 LTS. We've been also improving a lot of the, people were complaining a bit that we are these little things missing for years. Actually, Shader Graph is the biggest release in terms of feature in 6.3 LTS since we actually released Shader Graph. So you can expose, for example, your properties of a subgraph, and they will be directly exposed on the root parent without doing any rerouting. I will show you the Shader Graph template window. Oh yeah, sorry. We have a lot of swap of HDMI cables, so it's a bit tricky. So you can now, if you go and create a shader graph, you can go here, create shader graph, and you create it from template. And here you can see that you don't start from scratch. You can actually start from a fully functional lit basic, a 2D sprite lit, a decal, particle, a terrain sample, and so on. And you can even expose your own templates for your game if you want your team to only use a few templates. OK. So the second part was new visual features. It was not really the focus of Unity 6. But we still had some good improvement. Adaptive prop volumes, I will cover this in the end. And we had a bit of improvement in HDRP, improving the water system and the sky, bringing some night sky. But really the big focus of Unity 6 was performance. And we know that performance is death by 1,000 cuts. You cannot just do this thing on the GPU, and it will increase performance if you're CPU bound. And it happens in many places. These are almost all the things which are coming new in 6. And what is in purple is our new in 6.3 LTS, and it's going to be what we will cover a lot in this talk. And I will leave the mic to Damien to cover like what's new on the platform side.
Thank you, Matthew. So I'm Damien. I work with our platform graphics team. Our team's job at Unity is to make sure your games can run efficiently on as many devices as possible. And in recent years, we've been focusing on transitioning Unity to modern APIs like Vulkan for Android or DX12 for Windows. Older APIs, like OpenGLES, are actually reaching their end-of-life cycle. So you may even see on the latest Android version, some GPUs may actually no longer run native OpenGLES. They would actually use the angle translation layer, translating OpenGLES to Vulkan. And with the modern APIs, we can actually access the latest hardware capabilities, which we can use to optimize our graphics rendering in some ways we'll see in this session. Now, starting with Unity 6, we support the new WebGPU graphics API. It is actually implemented by libraries like Google's Dawn, which translate WebGPU to native graphics API calls on your device, like Vulkan or DX12. So the browser can also access the latest GPU capabilities. And one of the nicest additions of WebGPU compared to WebGL is the support for compute shaders. So we can offload high-frequency calculations to the GPU to be processed in parallel with very high throughput and use it to optimize parts of our graphics pipeline. And a common one is for compute or GPU skinning. We can transform our vertices and our blend shapes directly on the GPU and improve character performance. Or we can use this to implement compute-based particle systems like VFX Graph, which allows us to process our particle simulation, again on the GPU, and indirectly render millions of particles very efficiently. And we can actually look at a little example. If I open this demo project here, this is the spaceship VFX demo. It's originally for the high definition render pipeline. It's a quite detailed scene, but more importantly, it has a whole bunch of VFX, like this visual effect here. Now, traditionally, we could not easily build and run this on a browser. In this case, we would have to re-implement this effect using CPU-based particles. We would increase our CPU workload. It will also require some work. But with WebGPU, you can just very easily build and run this in a browser. So here I have my built demo in the browser. I have all these really nice-looking particle effects running really fast, very efficient. And I also have access to more features. Like I can use deferred rendering in this case. So I have a larger amount of lights, rendering very efficiently. I can essentially have PC or console-grade graphics in the browser rendering really fast. So that's nice. Going back to our presentation. One of the main challenges we had moving to modern APIs was the very fragmented ecosystem of devices, especially on mobile and Android and even on PC. All the devices may have outdated graphics drivers or may not support all the needed capabilities. These devices may actually run faster or even just more stably on older APIs. So starting with Unity 6.1, we actually apply what's called graphics device filtering. First for Vulkan. We can use Vulkan on newer Android devices or GLES on older ones. And with 6.2, we also do the same for DX12. So we use DX12 on modern machines and fall back to DX11 on old ones. And there's some default recommendation or min specs, but you can also set your own device filtering rules based on a whole bunch of properties, like the driver version, operating system, and so on. And this can be especially useful if you have a well-established game. It's running on a lot of devices with all APIs, can gradually transition to the new ones, starting with the latest driver and operating system versions, and then slowly reduce the min spec until you reach a recommended setting. So you can transition with less friction. But we can also control not just the graphics API, but the actual CPU threading mode. So modern devices usually have a higher core count. They can benefit from more aggressive multi-threading with what we call split graphics jobs. When we do a higher degree of multi-threading, we also usually use more memory. We allocate more resources per thread to avoid race conditions and so on. And all the devices may be much more limited in memory. So for those who may want to prioritize memory usage over CPU performance, with this system, we can very easily fine-tune between that. And just talking about memory a little bit more, because it's often a performance bottleneck. So on your average PC, you have a dedicated GPU with a very large amount of dedicated graphics memory, VRAM. which the GPU can access very fast with very high bandwidth. The latest, most powerful GPUs can exceed 1,000 gigabytes per second of bandwidth. But on mobile, we have an integrated GPU, which often needs to access system memory directly. And this bandwidth is also shared with the CPU. So we're much more limited in bandwidth. It's often a performance bottleneck. But even on a dedicated GPU, if we exceed our graphics memory budget, the system will transfer the excess data to system memory over PCI Express. And with PCI Express 4, 16 slots, for example, we have a max theoretical limit of 32 gigabytes per second of transfers per direction. If we frequently hit PCI Express and system memory, the GPU, the shader cores, will often have to sit idle, waiting for data to arrive from memory. So we have a lot of wasted GPU cycles and much, much worse performance. So we really would like to stay within our memory budget. And there are a few things we recommend doing. Textures and high-resolution textures can often use a lot of memory. Should always use texture compression when we can, like ASTC 8x8 will reduce your texture size in memory to 1/16th of the original size. Also recommend using MIP map streaming. You can set the runtime memory budget for MIP levels, and the system will automatically evict MIP levels when you exceed the budget. But starting with Unity, with the recent Unity versions, there's another thing we can do to easily control our texture resolution. So if I go back to my demo, if I look at the quality settings, it's under Project Settings Quality, we have the global MIP map limit here, which I can set to 8th resolution. Now everything is low resolution. And if I really zoom in, I see this table looks really bad. But I can actually set MIP limit groups. I can set different resolutions for different groups of assets. So I can set here a group for hero assets, for example, and I can set it to full resolution. Then if I just click on my texture here for the table, I can set the hero asset group and just quickly apply, and it's using high resolution. So this is just a quick way to set the resolution for textures for different parts of the scene very quickly. Another common good practice is using channel packing. If you have a whole bunch of texture masks, try to pack them into different channels of the same texture. You'll end up using less textures. Then we also have render textures. So the render pipeline will actually allocate a whole bunch of render textures, usually the size of the screen resolution. The higher the resolution, more memory we'll use. We can reduce the render scale to reduce the size of these textures. This will also reduce our image quality. But then we can use upscaling filters like Unity's STP upscaler in Unity 6 to maintain good image quality when upscaling to the final display resolution. Next up, we have graphics buffers. So in our C# scripts, in our rendering scripts, we may often allocate our own compute and graphics buffers. But most graphics buffers are actually managed by the engine and the render pipeline itself. And the number of allocations will grow based on our rendering complexity. A good example is with visual effects. If we have a lot of visual effects, the VFX Graph system will allocate a lot of buffers. You can actually use VFX Graph instancing, so the system will allocate shared buffers, which are used across multiple instances of the same visual effect asset. If you have a lot of visual effect instances, you'll save a lot of memory. And lastly, we have what we call scratch buffer allocations. This is what the engine allocates when we make draw calls, when we bind shaders. So if you have a lot of draw calls and you bind a lot of shaders and you have poor draw call batching, this will increase your memory usage with a lot of buffer allocations. And when we allocate tons of buffers, the buffer alignment also has a big impact on our overall memory usage. When we use large buffer alignment and we allocate a lot of buffers, we'll have a lot of buffer alignment padding, a lot of memory waste. Now with APIs like Vulkan, we actually query from the driver the recommended buffer alignment. For buffers, it's usually very small. But in DX12, we actually had a problem. For a long time, DX12 enforced a 64 kilobyte alignment for buffers, which when you make a lot of buffer allocations, you have a lot of memory waste. And when we look at complex games, they can often make thousands or more buffer allocations. This resulted in a lot of waste, but with the latest Agility SDK in DX12 versions, there's now small buffer alignment for DX12. So if we actually profile games like No Rest for the Wicked by Moon Studios, we save more than 2 gigabytes of VRAM just with that. It's a very important optimization. It's supported by the latest drivers, by major GPU vendors. Just make sure you update your drivers. And lastly, I'll talk about shader compilation. So in our project, we have a whole bunch of shaders. The editor will actually compile thousands of different permutations or variants for different static branches of the shader, for different combinations of effects and features. And compiling thousands of shaders can take a long time. Now, one of the most effective ways to reduce shader compilation time and the number of variants is by using dynamic or uniform-based branching. So we can control the behavior, the logic of shaders without actually compiling additional variants. And with 6.1, we can just do the same thing for fog, shader keywords. Just for this feature alone, it can cut the build time by 50%. We can also use dynamic branching in shader graphs very easily with Unity 6.2. And with 6.3, we now have these new shader build settings. So you can very easily configure your shaders, your keywords directly in the editor without modifying the shader source. And this can be fairly powerful. If I go back to my project again, just to see how we can use this, can very easily just make, in this case, a fast build profile, I called it. And in the settings, I selected a bunch of keywords like fog or reflection probes, and I set them to dynamic branching. And now my shaders will build much, much, much faster. Now, on older devices, especially older mobile devices, dynamic branching could potentially reduce my GPU performance. You have to profile, it's a case-by-case basis. But because of this, I can actually make a performance profile instead. And in this profile, I would set the same keywords to multi-compile, to shader variants. So you can very easily fine-tune between shader build time and shader performance. And I can even strip keywords. I can exclude the keyword directly from the UI. I don't need to write scripts to do that anymore. Another part of shader overhead is actually runtime shader compilation. So at runtime, we have to pass our shader program to the graphics driver to compile the hardware binaries for the shader, which can take a long time. You'll see these big frame time spikes in the profiler. On modern APIs, like Vulkan, we actually have to create a pipeline object. So in addition to the shader, we also need to specify a bunch of graphic states, which can actually change at runtime. And with Unity 6, we now have this new graphic state collection API. We can actually trace all the PSOs that the game is using, save them to a collection. We can then pre-compile this collection to cache our PSOs and our shaders. And if we look at the example of this mobile game, Sniper Legends, what it means is whenever I shoot this zombie here and I change the graphic state, I have a much smoother transition. I no longer hitch or stutter. So you can have much smoother, more reactive gameplay. And we'll use the graphic state collection to create PSOs on modern APIs. With 6.1, it also works on older APIs using shader warmup. So you can use the same workflow across all the new APIs. You can transition easily. And with 6.4, it actually also works on WebGPU. So I can actually go back to my demo and see how I'm applying it here. And it's quite simple. I have this game object at the bottom. I call it graphic state collection with this collection script on the right. It has two modes, tracing and warm up. So in tracing, I'll just play through the build. It'll collect the PSOs and then save them to this asset, to this collection. And if I use warm up mode, it will just warm up the PSO. And I can actually look at the script just a minute. It's actually quite simple. On startup, I basically just create a new collection for my quality level and just call this function to begin tracing. And then tracing will happen automatically. It will trace the PSOs. When I actually lose focus of the application or destroy the component, I send it to the editor to be saved as an asset in my asset folder. And lastly, to actually warm the PSOs, again, it's quite simple. Here I just set some optionally some UI, just so I can track the progress of pre-compilation, fetch the collection, and then start a coroutine to progressively warm the PSOs. So I can do it over time. I can warm 3 PSOs at a time each cycle with some time delay in this case. I do this to stretch the PSO warm-up over multiple frames. And what it actually looks like when I start the demo, I have this progress bar on the top right, progressively warming the PSOs. I do this to avoid warming all the shaders and PSOs all at once, to avoid blocking the application. I can do it more smoothly. I can also do it asynchronously in the game's background. And that's it. I'll hand it over to Oliver.
Perfect. Thanks, Damien. So let's have a look at our rendering setup. First step is to pick a renderer. For budget mobile, and in most cases for XR, we recommend URP's forward renderer. And for complex dynamic worlds, where you have many real-time lights, we recommend deferred plus or forward plus if you require per light processing, for example, when doing non-physical stylized rendering. And this can also be used on untethered XR. If you require off-the-shelf advanced shaders, lighting, and effects on PC and consoles, use the HDRP renderer. Note that we have rebuilt the core architecture of Unity 6 on the render graph system. And this is now unified between URP and HDRP. And that's in 6.3. It allows render pipelines to be highly optimized and configurable. And since we are now render graph only, we have removed over 12,000 lines of code from URP, which leads to faster iteration and smaller build sizes, which is especially important for the web. And overall, this is now also cleaner to understand because you don't have the legacy APIs anymore that confuse developers. Here's a typical example of being CPU bound, where optimizing your render thread is really important here. In this example, we see that most frame time is spent processing in the render loop on the main and render threads. If we can reduce that latency, we will submit commands faster and improve our frame rate. And we have multiple techniques to optimize the CPU rendering processing. First, we have the SRP batcher. And all material data is then cached on the GPU. And this allows them to send and draw all geometry with the same shader at once. And in Unity 6.3, we have now the ability to add variants to these batch renderers, thanks to a new feature called RSUV. I will show more details about this in a bit. And to optimize our rendering further, we have the batch render group API. And with that, we are now also storing all geometry information on the GPU. And then, by leveraging burst, we can generate the rendering commands in a highly parallel optimized way. The GPU resident drawer system, introduced in Unity 6, will do that automatically for you. And that's when you use game objects. So the batch render group is basically for dots. So you don't need to interact with the batch render group yourself if you use a GPU resident drawer. And finally, on Vulkan and DirectX 12, we can also send our drawing commands in parallel to the GPU thanks to split graphics jobs. Now let's have a look at the RSUV feature that I mentioned. So we have, again, in the package manager, a new sample for this that you find in the universal render pipeline. It's called renderer shader user value sample, because we are very good at naming. That you can import, that I have here on my laptop. And it shows a bunch of characters. And they are all individually dressed, basically. So they have different skin color, different hair color, cloth color. They have different headgear, and so on. And this is all controlled through this example script here. So it's basically on the CPU, we define how a character looks like. And then if I look into the function update renderers, here we can see the new API. It's basically for each renderer, you can set a shader user value. And that's just an unsigned integer, and you can encode any data that you want to send to the GPU to then process it in your shader to, for example, to add variations and still don't break the SRP batcher. So here you can, for example, see how the skin color that I was selecting is then encoded. So we have a helper class here to encode data in this integer field that you can then pass to your shader. And we also, in this example, control the animation of each character. For example, you can click on one, and then it's jumping. So you can also send like more data and then use the offset in the vertex animation, for example, for this. And the nice thing now is that if I look into the frame debugger here, I can see that I still draw the whole characters just in one batch. So there's one batch for the hair and one batch for all the characters here, because they have one shader, but I can still now add the variations, and that was before not possible. Before, you had to either use multiple materials or you break the batching. And if we would break the batching, if I, for example, disable the SRP batcher, we can see here now that each item is drawn individually. So instead of 4 batches, I have 241 now. And this could happen if I accidentally break the batcher with each soldier. And next, when you then want to optimize your scene geometry further, I talked about the GPU resident draw already. This can then further improve the CPU rendering by just enabling it. It's basically just a drop-down that you can use in your URP asset. And as you can see here in this benchmark that we got from Lego, utilizing the GPU resident drawer vastly improves performance when rendering a large number of Lego bricks. And you can see how the system removes the heavy load on the CPU by drastically reducing the draw calls so that the bottleneck shifts to the GPU. And from this point on, they can then use GPU performance optimizations to further improve their rendering. Because now that our rendering is set up, we want to render all the pixels on the GPU. And especially if you are targeting battery-powered devices, energy-efficient rendering is key. Unity operates totally optimized on the full device spectrum. Consoles or high-end GPUs consume up to 500 watts, are always plugged, and have massive cooling. An average smartphone has around 5 watts, has no active cooling, and you want to last it the whole day, so we cannot waste any energy. And the challenge we face is not only about battery life, but mainly about heat. So we optimize Unity to reduce the heat we generate. Because otherwise, the operating system will throttle us down to prevent damage of the chip or battery drain. And if it would not do that, we could basically call this talk "blow up your graphics," and they would be literally on fire. And that's because a lot of energy is consumed through memory bandwidth. To address this bottleneck, most mobile GPUs apply a tile-based rendering architecture. This works by dividing the screen into multiple tiles, and the GPU then in parallel rasterizes and shades each tile independently. And since the tiles are relatively small, they can fit inside the fast but limited on-chip GPU memory. And we can then, after each tile is shaded, optionally choose to store the data in the system memory, for example, if you want to use them in following render passes. But since then all the pixel information needs to run through electricity through the chip, we increase our memory bandwidth, and with that also the temperature inside the system. And as I pointed out earlier, in Unity 6 we now have the render graph backend. It makes passes modular and composable by handling dependencies centrally. It reduces the overhead by merging compatible passes without and managing the resources automatically. And developers can plug in custom features without worrying about texture lifetimes. And then at the core of on-tile rendering are the native render passes. It allows us to take full advantage of systems like Vulkan subpasses in order to reduce the memory and achieve efficient rendering. With RenderGraph, URP tries to merge passes automatically so that they stay on tile and there is no costly reads and writes between tile memory and the system memory. In this example, we compare the built-in deferred versus URP deferred on an iPhone 14 Pro. And the result is 60% lower bandwidth usage. All the G buffers stay on tile, and that is a huge improvement, clearly visible here in the timeline. URP can be a very minimal pipeline in its leanest configuration. And then it scales with more effects you are adding. And then with adding the effects, you can then get most out of your target platform. In Unity 6, we can easily visualize in one view how different URP settings change the rendering of your frame. And that can be done with the render graph viewer that I want to show you in the editor again. Okay, so what you see in front of us is the render graph viewer, and you can find it under Window, Analysis, Render Graph Viewer. And what it shows now is for my current frame that we see here in the bottom is all the render passes on the top. And we see here that there's a blue line under a few render passes, and this is the main where we draw our objects. And they are all mergeable into one native render pass. So they don't consume any bandwidth, so they are mergeable. And then on the left, we see all the resources that are used by these render passes. For example, we see that this is quite a minimal pipeline because we are writing directly to the back buffer here. So red square means we write to a resource, and green means we read from it. And if I now enable any feature in URP, for example, the depth texture here, I see that my pipeline changes. So the first thing is that we notice that the blue line is broken apart because we now do a copy depth here, so that we inject a render pass in between. So we are now already generating more heat and more bandwidth, basically. And the second thing we see is that the graph also grew vertically. And that's because we are now not directly rendering to the back buffer anymore, but to what we call intermediate textures. So these two textures here are now where our main rendering happens. And this is the case because we here want to read from the depth texture to copy it into a global texture. And then finally, we also need to blit back to the back buffer. So we need to read from our intermediate results and get it back on screen. So here you see already how the graph changes just by clicking one texture. And depth texture is, for example, useful if you want to read the depth in any of your transparent shaders to create effects. But maybe you don't want this in transparency, so you can also do this after transparent. And then you see that the copy depth is happening later. And then at least our opaque, skybox, and transparents are merged again into one pass. So it's always a great tool here to see what you should change. Another thing we can also easily see is now, if I switch from forward to deferred, how our pipeline changes like quite a lot. So we see totally different render passes now here, and here we also see more resources. But what's nice here now is that we see that these empty squares here are actually memoryless textures. So these are all the lighting relevant data is in these called gbuffer textures is stored here, but they don't consume any memory because they stay inside the tile. And that's because we read them through frame buffer fetch that is indicated by this F symbol here. So we only read the local pixel information from the previous render pass, so we don't need to load and store the thing. And what's then, if we then enable, for example, post-processing, we see again that the graph changes, so our render pipeline really adapts. And for example, here we see that the post-processing is happening here. And we have also some preparation passes. For example, the bloom is generating like a lot of resources here for the bloom pyramid in order to prepare the post-processing. So if I would disable bloom, I see that again, the render pipeline adapts and needs different resources and can optimize itself again. And what we notice here again is our empty square that we saw at the gbuffer textures earlier. And that's because for the depth here, where we have, that's our intermediate texture, we are currently not reading from it in any post effect. So it can stay fully on tile because we don't want to use it anywhere else. But if I would enable this depth of field, for example, we see again that our pipeline changes. But now our camera depth texture is not memoryless anymore, so we read and write into system memory. So again, something where we generate bandwidth and need to look at. And then we have also, if I disable the post-processing again, because there are post-processing effects that can stay fully on tile and are fully memoryless, because they don't need any neighboring pixel and information. And especially on untethered XR, we have for that a new feature called on-tile post-processing for untethered XR. And this can be used to use supported effects like vignette or color grading and so on in XR. Let me show you this on the slides. Because here again, this is a new feature, by the way, in 6.3, and it's available for untethered XR. And here we see again that both our intermediate texture have an empty square, which means they are not stored in shared memory. And all the drawing, including the post-processing, is now done in a single render pass, as you see again by the blue line. And there is no final blit to the back buffer, so because that would break the tile rendering again. And on untethered XR, this is very important, because, for example, on MetaQuest 3, for each eye, you have a 2K by 2K render texture. In 6.3, we also have a new feature that you can connect the render graph viewer directly to the device to inspect how the hardware is rendering your frame actually, so you can inspect this more clearly. And the comparisons here highlight the gains in frame time and bandwidth savings. And this feature also unlocks HDR rendering in XR with good performance, making richer visuals practical here as well. You have seen how the render graph viewer can help you understand your frame. Another important thing that not everyone is aware of is the rendering debugger. For example, here we can visualize overdraw, that is a common reason for pixel overhead. It reflects the amount of pixels shaded compared to the final output. And to mitigate this overhead on PC and consoles, we recommend enabling a depth prepass. While on mobile, this is not recommended. And that's why you should keep transparent materials there to a minimum. To analyze the commands being executed on the GPU, we use a third-party tool. We can use third-party tools such as RenderDoc. In this example on the right, we see the quad overdraw, where small triangles are processed multiple times for 1 pixel. So we may want to rework this mesh for larger triangles using LODs, or with our new meshlot system that we introduced in Unity 6.2. Here we are seeing a scene that contains lots of props and lots of characters. To generate the LODs, we just click the Enable Generate Meshlots button, and then we can inspect the LODs for each mesh individually. And it works with static and with skinned meshes, as you can see here. And each LOD tries to keep the best visual quality while reducing the number of triangles. With the scene as complex as this one here, we can go from 81 million triangles to 4.5 million triangles without downgrading the visual quality. And Meshlot is a new lightweight LOD system, and that is complementary to LOD groups. And now that we have discussed all the techniques to optimize your rendering, let me hand over the mic again to Mathieu for an awesome live demo how you can set up your lighting in your scene.
Thank you. It's cool, we're on time. Is it okay? It's a lot of content. I hope it's good. Okay, cool. So maybe I will sum it up because we have a bit of time. So like where we are with C.3 LTS is that you can rely on the modern APIs. So you can actually activate DX12 in your game, and we will fall back to DX11 on the devices which don't work for you. Same thing for Vulkan. It will fall back automatically on the GLES devices where this modern API don't work as good. You will be able to improve your build time by reducing the number of shader variants because you have more control on the keywords now, and you can leverage the build profiles for this. Oliver, you showed how to actually improve the batching with RSUVs and how to, what did you show?
Visualize like how
and how to configure your pipeline. Because you see that it's very important. You know, in the past with built-in render pipeline, and even at not a long time ago with URP, you could not actually understand what is happening under the hood. Now you really understand what is happening, and it makes a huge difference on the performance. And we have been focused for years on optimizing the end, when actually the inside we didn't understand. And one checkbox can change everything. So I hope like this gives you a lot of performance. I will just show you a small live demo about lighting. For this, I will use a few nice assets, the classroom from Blender, the low poly mega city, also the Azure Sky system, which is not mentioned here, and one polyhaven asset. Sorry. Okay, cool. I was starting to panic. My computer didn't turn on, but it's good. It's almost good.
It should come back.
That's so this is our new color grading algorithms.
There it is. There it comes.
Okay, it's coming soon. So I will use first. I will use a starting scene. So I mentioned to you that we have shader templates. We also have VFX graph templates. Same thing. You can create a new VFX graph and don't start from scratch. You can choose from presets. And we had scene templates for a while. We have two new scene templates which are really nice to use, an indoor and outdoor one, which are actually common between URP and HDRP, so you have the same look if you put your assets in. So I'm using the outdoor one here, and it's already set up for good lighting. So if you want a good reference of good lighting, you can do this. It's nice to do, for example, look dev, so I will take this marble bus from Polyhaven, and it directly looks good. It just gives you like a good starting point. By the way, we mentioned mesh load. So for example, this Polyhaven asset has no LODs by default. It's 17,000 triangles. I will just generate the mesh load, show you that it's there. So it's a bit long, the generation, you will see. Oh, no, it's done. And now we have already like different LODs generated for you. And so mesh load is actually not LOD group, it's a complementary system. Where the goal is to have no transition because we actually collapse the triangles. We keep the original triangles of the mesh. We just remove some of them as they don't become important because they are too small. So for example, if I take the marble bust, we have it's funny because like people thought it was not working because you don't see the difference. If you go in wireframe, you don't see the difference because you don't see the difference. There is no difference. So we had to add this little thing here to say that mesh load, it's mesh load 0 and then it's mesh load 1, right? And people were like, no, it doesn't change. And so it's really nice because you can just select your objects now and it will be automatic. It's very conservative. So you might have mesh load just popping a bit far away because we actually don't change if there is a discrepancy. Okay, let's move to actually glowing up a bit the lighting. So I will remove the geometry. And what I really love is starting from scratch. So I will start to do a kind of 101 of lighting in URP. Because if you want to know how to light, you need to know exactly how it's working and maybe why it's not working in your case. So I will remove all the lighting setup in this scene. And the best way to learn about lighting and especially global illumination is, sorry, not this one, is to use a kernel box. So we can really start from scratch here. Here, in this scene, we have only one thing, which is the sky. And the sky will generate an ambient probe, and which means that every surface pointing down will be in brown because the bottom of the ambient probe is brown. And the one facing up are blue because the ambient probe coming from the sky is blue. So if you want to change this, you can, like for example, if I change this crazy sky, which is red on the top, you can see that it actually doesn't change the ambient probe. And here it's very obvious that it doesn't work, but when you have a full scene, you might actually totally miss that your skybox is not the right one. In URP, you need to bake the ambient probe so that it changes. You can also write a script if you want to have a time of day to change it, but by default, it's not changing if you don't rebake the lighting. So now the next step, of course, is these things shouldn't be brown, right? Because there is a ground floor in between this and the bottom of the skybox. So in this case, I will need somehow, like in raster rendering, to send rays and to kind of know that there is something underneath. And usually to not cost anything at runtime, and because it's not really possible otherwise, I will bake the lighting, right? So the first thing to bake lighting, what most people use, because it's the cheapest in terms of performance and the best in terms of quality, because you can bake shadows, ambient occlusion, and indirect lighting, is to use light map. One good view to look at it is this view here in contributors receiver mode. You can understand how your geometry is contributing and receiving global illumination. It's very important because if you start having little objects receiving light maps, it will take hours and hours to generate light maps when it's not needed. Here, it's very important to choose the right one. So here, everything is just receiving global illumination. Since nothing is baked and nothing is contributing, nothing will work. So I can just go here and select contribute global illumination, and I will receive this lighting from light maps. So again, it's a bit long to bake. No, I'm joking. Because it's like we have a new GPU light baker. So you see, it's really took like a few seconds. And now we can see that it's good. The contribution from the sky is removed because we don't see the sky inside of the box. Now we see that these objects, which could be your character or dynamic objects, are still lit incorrectly. We still see the blue contribution from the sky. It's something, again, like you might not see it in your game if you don't enter like the right debug mode to visualize it. By the way, since I have a bit of time, you can use a rendering debugger, and in the lighting tab, you can use the global illumination. Oh yeah, I didn't prepare it, so it has to bake the... But there is a very nice mode to compile the rounds. It will come. So like here, this object is brown on the bottom and blue on the top, which is not correct. So usually what you do for these objects, you create light probe groups, right? So it's here. There will be little probes that are placed in the world and kind of fake the global illumination and just relight, like little lights that will relight the objects. It's nice, but I have to place these probes by hand, right? You can edit them here, and I could duplicate and place them, but it's a bit long. If I do a live demo, I won't have time. So I have prepared it for you, and now I've placed them, and I can rebake the lighting now. And we should see also it's pretty fast to bake. That these objects, oh no, sorry, I didn't turn it on actually. And here, so now you see that they are properly lit. The objects can move around and not take any contribution from the sky. So let's go to the next step. Now, like you see how important already just the sky setup requires some things. So let's just move to the next step where we start bringing a directional light. You can see here that the 3.4, which is pi, is the difference between URP and HDRP reference lighting. That's why it's here. I will just go to like something different to be more interesting in terms of lighting, and I will let the door, let the light open, like start going into this room. So what I want here is that the light is bouncing on the green wall and lighting back this little cube here. And it's working automatically. You can see already like all of this is contributing to the quality of your visuals. You can see that it's kind of slightly green here on this side, and if I move it on the other side, it will be slightly red, lit by the probes. So you think that everything is well, right? There is one limitation to light probe groups, is that if you have a larger object, so let's say I duplicate this like composed of multiple objects like this, we can start that there is a small problem with light probe groups, is the fact that each object is sampling the probes around it. We can see the sampling here, which means that you have discontinuity between two objects, and it might not look really great, right? Which means like light probe groups are limited in terms of the size of objects you can do. It will be nice on very small ones, but not as good on bigger ones. So to compensate for this, we have, like for these two things, manual placement, which is a pain, and like the visual fidelity that limits the size of objects to be baked. We have introduced a new system called adaptive probe volumes, and it's very easy to use. You just place a volume here, and then in your settings, you go into the light probe system, you change it to adaptive probe volumes, and then you bake. Again, like to visualize these probes, you can go into the rendering debugger and in the probe volume tab, and you can display the probes. And we can see here it's magical, no manual placement, It's also adaptive because it places less probes where there are no geometry and more probes when there is more needed. We can see now that this thing now is totally continuous, which means like you can really light larger objects with adaptive probe volumes compared to light probes, which means that you don't need to bake as many light maps. Like you can just bake light maps on the much bigger surfaces, which is a huge gain of time. Actually, in this scene, because we still want to have shadows and ambient occlusion being done like real time, we can actually light the entire scene with the adaptive probe volumes. So again, we go back to our debug view, and we can just say that this entire scene here is actually lit with only the adaptive probe volumes. So let's look how it looks here. You will see it's almost the same, right? I don't know if you see that there is a problem. Do you see that? So there's something not really cool here, the white, and it's called light leaking. And in any probe system in the world, you have light leaking because you place probes, and of course, at some point, one probe is outside and another probe is inside, and the light leaks inside. So with adaptive probe volumes, we have multiple mechanisms to prevent light leaking automatically. We have virtual offset dilation. So already most of the leaking is handled. But since it will always happen at some point that you have some light leaking, and instead of placing manually the probes, we offer a way to assist the baker for you to remove the problematic situations. So here, for example, the first thing is to understand why there is a problem. So you can go in the debug probe sampling and just go there. And you can see that if we sample this place here, that it's sampling probes outside and inside. So it's exactly what we meant. So what we want to do is to just put a probe volume here and say, don't generate probes too close to this ceiling because we don't want to have leaking. So now, if I bake the lighting, we can see that the problem is gone, and that's good. Now we can, like the problem with light baking is the fact that it's always for static worlds, which is nice. One thing that that adaptive probe volumes are bringing is the fact that you can actually go into this system here and say enable lighting scenarios in your settings. And now you can have different baking scenarios. So you can have like 12 and 2 o'clock and 4 o'clock, and then bake different scenarios, and then you will be able to blend them to have a time of day. We can also have another system which is called sky occlusion, where you can bake the visibility of the sky, and then in your shader, knowing how much of the sky you see and knowing the color of the sky, you will be able to change the lighting inside of the building as the time is changing. Now, there are moments, and we hear this all the time, that, oh, I cannot bake lighting because my world is changing and so on. So I have something like it's super exciting. It's the first time we're showing it ever. First, okay, I tease you. First, you have a volume so that you can remove the contribution. You have more control actually on adaptive probe volumes. You can have a lot of control. So I will remove it, right? And we have a new system. It's called Surface Cache Global Illumination, and it's a real-time GI system. It's pretty cool. Are you ready? Okay, we turn it on. We have GI. So the same thing. Okay, cool. But I know why you're not clapping that hard, because the scene is not amazing, right? Like it's Unity is doing his new tech demo, and it's woo, blue, red wall and green wall. So I got this covered for you. We should have a nicer scene. I mean, it's already great that just one button is lighting this scene, right? But we can do better. So this is where I will take the Blender scene. Okay, here. Just need a bit of preparation. And let's bring the classroom scene. So, I have still the debug mode enabled. Okay, so here we can see that the lighting is wrong. It's typically what you see, what I explained before. You have a mix of things which doesn't correspond to your lighting. So, to show you that I have no baking in my sleeves, and I don't have sleeves actually, I will clear the bake data, and I will enter play mode. so that we're sure that we are real-time lighting, right? So I will, something in the corner, I tease you always. Be careful sometimes with the AC's tone mapper, because it can really darken the scene. And here, for example, we can see that also we have lighting contribution from the fog. So I will just remove it. So okay, we have this scene now. Are you ready? Okay, and voila. So it's really cool. But we are not at the end of the talk. So what is really great is really this typical scenario, because it's real-time lighting. You know, like you have a game, and in your game, somebody decides to put a cube in front of your window, right? And yeah, it's pretty cool, right? And we are not at the end of the talk. Still, sorry. So I'm getting over myself. And maybe you have a time of day, right? So you want to go in the evening, and then put the sky here. Wow, you see? Sorry. What can we do? Okay, just a little thing. It's like we can just finish this scene with a bit of screen space lens flare just to make it totally shiny. And then, okay, it's almost here. To finish that scene, we have this nice little, oh, we don't see it on the screen. Okay, we see it a bit. Let's boost it actually up. Here, cool. Nice, okay, and you think we are at the end of the talk, but we are not. The thing is, like you will say, okay, it's very easy to have a small scene like a classroom, right? How does it work with a bigger scene? Let's see this city. So it's called the Low Poly Mega City from the asset store. Super nice asset. And we use the Azure Sky Manager also here to manage the sky. So in this scene here, you see it's a pretty large scene. There is a stadium, an airport, a residential area, like the harbor and so on, right? And let's see how it goes. Like on such a big scene, right? Okay, 1, 2, 3. Like look at the occlusion here. Wow. And now that we have this, we can go there. And you see before, after. And we have a time of day now, right? We can just change the time on this huge city. And you see how beautiful it looks. And as I mentioned, you know, sometimes you cannot bake lighting. For example, you have an RTS, you have a simulation, you have like a city builder. So we just built a little city builder for you here. I will just place a few buildings dynamically. Where is it? Where is my? Yeah, here, for example. And I place this one, and you see how they seamlessly integrate into the world. I have a little cafe that I really love to go to here, right? And all that works seamlessly. But you might say, okay, it's a small game. What about my first-person game, right? Let's just enter this world first-person. You can see that the light is bouncing on the red building and lighting the building on the side. The building that I just put now are totally integrated. If I go indoor, like this is actually, like all the city has indoors. I can go there and I can put a quad and it will light this scene. Something important, yeah, thank you. Something very important here is like, you see that the quality is not perfect, right? Like, and it's actually something voluntarily. When you make a real-time GI system, the problem is like, if you cannot run it for all your game, like for all your players, then you will have to have a fallback and then you cannot actually use it. So what we've done is to design it so that it can run from high-end mobile to high-end PC. It's really like our goal is to be there. It's not to have the perfect visual fidelity, but it's to run on as many platforms as possible. I will just finish by just going around. For now, we only support the directional light and emissive lights. We will work on point lights, but just look here. You see this light? It's just coming because this car here has emissive triangles. We can actually go in the city, and now it's purely lit by these emissive signs. It looks super Like, I'm super impressed, honestly, myself, when I've been working on this demo with the team. Rasmus is in the room. He has done an amazing job driving this feature. You know, like here we can change the time of day, and it goes from being lit by the sign to being lit by the bounce on the umbrellas, lighting the building in red here on the side. I will finish here. I'm exactly at the time. By the way, you know, it's running on my laptop here, which is a 1050 RTX. And it's actually not using RTX at all. It's all implemented in compute. There will be a fallback so that it's even more accelerated when you have RTX. But it's very impressive where we are now. Look at this beautiful scene. Yeah, super excited about it. Thanks a lot.